Today we're talking about Taylor series, specifically the derivation of the Taylor series. I don't have any notes with me, so I'm hoping that this will go smoothly. I consider the Taylor series to be probably one of the most amazing things in math, and it's like it looks complicated at first, but it's actually, the idea is pretty simple. That is, if we have some sort of complicated function, like some sort of function we want to find the value of that isn't easy to find the value of by hand. That's the original motivation of the Taylor series. Like, say we wanted to find the sine of 0.1 by hand. So as you might know, it'll be kind of hard to do that, but people back in the days used to look at tables and stuff to figure this stuff out. But and it's funny because the original motivation for the Taylor series is to be able to calculate these types of functions like this by hand. But these things, Taylor series, they are incredibly important in physics and like anything. Lots of things you can approximate by the first few terms of the Taylor series. You'll get complicated differential equations that you can simplify vastly if you approximate them with Taylor series. You can rewrite functions in Taylor series. These things are just incredibly useful, and they never go away. And oftentimes a lot of people hate them because they're not the easiest thing in the world, and they want to just be done with it and shoo them off and hope to never hear from them again. But they don't go away. They're just so important. And basically the idea behind the Taylor series is, and I'm going to show a couple of pictures here I got from Wikipedia. We have, let's say, we have this function right here, the sine function, this blue one. And the idea is to find some sort of polynomial f of x that is equal to or very, very close to the sine function in a small domain, as you can see here, between like negative pi and pi. They're pretty much equal, and therefore we're trying to find a polynomial. Polynomials are easy to calculate by hand. So if we find this polynomial, it'll be easy to calculate sine, because all you do is just plug in the values in a polynomial, which you can do easily. So so what does that mean? How are we going to do that? Well, our polynomial, we're going to write p of x is equal to a0 plus a1x plus a2x squared plus a3x to the excuse me, sorry, x to the third plus dot dot dot. And it's just some infinite polynomial. We don't know how many terms it's going to be, and this is going to be equal to a function f of x. Now, in a certain domain. Now, what you do is you pick a value to quote unquote center the Taylor series at. Like, for instance, in this, the center is at 0, and as you get further from 0, it gets less accurate. You see, way out here, it's not accurate at all. So you pick a point to get close to, and you sort of equate the polynomial and the function at that one point, and then around the point they're really close, if not almost equal, or equal enough to get enough values. So now if you pick that point to be 0, it's called the Maclaurin series, and if you pick it to be anything else, it's the Taylor series. So For the sake of ease and I don't know. Yeah, I'm just gonna say ease. We're gonna pick the center at 0, but you'll see at the end that it really doesn't matter where we pick it. So we're gonna center this at 0. So that means that f of 0, from our logic before, f of 0 equals the polynomial evaluated at 0. So what does that mean? That means f of 0 equals, now you plug in 0 into this polynomial, this infinite polynomial. Well, there's an x in every term except for the first term, so the only thing that's going to survive is the first term, a0 or a0. So now our next leap of logic is, if these functions behave the same around a certain point, then it makes sense to say that their derivatives also behave the same way. Because if we go back to this picture, you know, the slope of the tangent line at 0 is the same for both the pink and the blue line. So that means f prime of 0 is equal to p prime of 0. But what's p prime? P prime is a1 plus 2a2 plus 3a3 plus 2a2x plus 3a3x squared plus dot dot dot. It goes on forever. We just took the derivative of this. So now we just plug in 0, and what do we get? We get a1. So now if the functions behave the same around that point, and that means their first derivative is the same, that also means that their second derivative is the same. So f double prime of 0 equals p double prime of 0, which equals, you take the derivative of this now to get p double prime. So it should be 2a2 plus 6a3x plus dot dot dot. Now when you evaluate that at 0, you get 2a2. And if you were to do this again, you would say f triple prime of 0 equals p triple prime of 0 by the same exact logic, and you evaluate at 0, you get 6a3. And then you keep doing it, you would get 24a4. Let me just write the whole thing out so it's more explicit. p4 prime